Many designs I see in buildings spec their machines to run at certain condensing temps, artificially high, like 95. Goodness, 95 degrees. Why not aim for lower temp you can manage or even get your condenser water down to true ambient, like 70? And this is a very good conversation that I don't know, there's the opinions around it could go a few ways. On one hand, I found that some sector of building energy optimization. So there are people out there that specialize in optimizing a building and their energy profile, which includes very heavily the HVAC system. But what I find is many of these people are looking far beyond just the HVAC. Their specialty includes a whole gamut of energy usage. There's a lot that goes into what they're gauging to control or help optimize the efficiency of the building. And what I have personally experienced with some of these is they do believe in either raising condenser water temps, it would be one, so that their idea is they're trying to draw load off of the cooling tower and make the fans run slower. That is the main concept that they've always given me, is they want the fans to run slower on the cooling tower, and so less amperage, less energy, right? If as if it was that simple. I'll get to that in a moment. You've experienced how difficult quality chiller training is to get. I've spent over a decade working as a chiller tech on everything from air-cooled scrolls to large-scale centrifugals in manufacturing facilities. I'm tired of seeing how hard it is to get quality training and support. So I built the resource that I always wanted. I'm offering the help you're looking for, and we can get started today for free. ChillerAcademy.com. Part of what they do is they'll lower the static set points on these buildings. That's something they'll do at the air handler levels, right? More than just try to get the condenser fan or the cooling tower fans to stage down. They'll also go as far as they'll start running super low statics on all of the air handlers so that they can slow down the air handler motors and, again, achieve, Energy Star ratings and all the other jazz that they go for. And so a building that needs to run 1.2 inches of static for smooth operation, they'll turn around and drop it to 0.8 and be like, oh, it'll be good enough. Industry standard is 1 inch, It doesn't need to be 1.2 is too much, even though, anyway, I'm get off on a tangent with that. I've had lots of dealings with energy management optimizers, if you haven't, and I've just, anyway. Here's my approach to this and pitch that I would give. Now, our ultimate goal for condenser water, so being the fact that we have condenser water temperatures, means that we've got a water-cooled system, period. Our goal, in my opinion, should be to try to maintain as low of a condenser water as that chiller is allowed to handle, and do that as effectively as we can so that we can lower the amps. Because in most cases, unless we're dealing with just really small equipment, in most cases, by a couple of degrees or several degrees of temperature change on the condenser water can mean significant load reduction on the compressor, because its amount of energy is directly correlated to how hard it's having to compress. So the higher we force our condenser pressure, the harder the compressor has to work in order to achieve the condenser saturation that we need in order to allow for the proper heat transfer process. If we are trying to save energy by slowing down a 50 horse motor in a cooling tower and dropping it by 10 amps, but that means that we're, instead of being able to run a 75 degree condenser water, now we're trying to run an 85 degree and just run that fan a bit slower, those 10 amps are substantially multiplied by a huge factor in the compressor, because now instead of trying to get that low pressure refrigerant to 75 degrees of saturation, Or I guess let's go to 3-degree approach here. Okay, so instead of trying to get it to 78 degrees of saturation on the condenser, now we've got to get it to 88 degrees of saturation. That's a pretty big difference. And that requires, 10 amps at the tower fan turns into 50, 60 amps at the compressor. Now, these aren't hard numbers. These are just examples, but this is realistic to what I personally have dealt with in these cases. It is way more efficient to put the extra load on the tower fan, and it's a hell of a lot easier to fix a tower fan motor than to try to service a chiller that's been beat to hell because we're trying to run high condenser waters. Whether it be a surging issue, that would be the worst case scenario, right? You artificially trying to use less energy in your cooling towers by raising the condenser water set points, but now you've pushed your chiller to a point where it's more frequently surging. Well, now you've substantially increased the likelihood that you're going to end up having a catastrophic failure due to the surging conditions, which is then going to turn into $100,000+ overhaul just to get the chiller back online, not to mention the downtime and everything else involved. Like, that's what we're discussing here. So to me, it makes absolutely no sense to artificially run really high condenser water temperatures just to save on the tower fan. And what I've seen is these people are good at their job most of the time, these optimizers, okay? So I'm not taking that credit away from them. And what ends up happening that I have seen is they'll do these things and they will end up showing where they've reduced the total energy usage of the building. And so they have this positive feedback loop to think that, okay, well, by setting that high condenser water set point, like that ended up, taking a lot of load off of that was part of the bigger picture to take the load off. And we're now more efficient because of that. When in reality it's all the other things that they changed to help that building operate better that did lower the energy profile, but they did end up increasing the chiller's energy profile because of that condenser water set point. And if they would have done a better job on the condenser water set point, they could have reduced that energy profile even further. But they don't see it that way because they just don't, they're not chiller technicians. They don't see it from our perspective, and that's okay. That's their job, and this is ours. And this is why we have to work alongside people like this to help mitigate these little things. So, okay, so I've gone on this whole spiel about set points and not artificially raising them. It's better to put load on the tower, not the chiller. What actual solution do I recommend? Like, what is my go-to with that? Well, it is having a variable condenser water set point. To me, this is the perfect middle ground. And all it takes is a temperature sensor and a relative humidity sensor on the outdoors tied into the control systems. And most control systems nowadays, especially just your regular PLCs, programmable logic controllers. So you're talking your Honeywells, your Distechs, your Johnson Controls, your Trane, like all of these have basic like control algorithms already built out for variable condenser water control. So once you have just the temperature sensors, it's not that hard to integrate the PID required to control this, the algorithm that we need. So you need to know your tower's approach. Okay, so tower approach is the difference between the leaving water temperature and the wet bulb temperature. That is your cooling tower approach. Most generic cooling towers are about 5 degrees of approach. Some really high efficiency ones I've seen get as low as 3 degrees. Some really beat up or older towers, or if they're not very well maintained, may run more like 7 degrees. So you do need to kind of figure out what is your tower approach that your tower is able to do. 5 degrees tends to be a pretty even baseline for most towers. So what you'll end up having is your control system can calculate wet bulb by taking the ambient outdoor temperature and the humidity, plotting that on or converting that into a wet bulb temperature via psychrometrics. Okay, very basic stuff. And then we can plug that to control the condenser water set point. So essentially it is wet bulb temperature plus 5 degrees, with a 5-degree approach, let's say, equals your condenser water set point. And let that be a variable set point. Okay. Now, I take that a step further to where we need to set some minimum and maximums based off of our chiller. So with a lot of chillers like your RTHD or a CVH, CDH, those cannot operate with cold condenser waters. They need that warmer water to maintain proper oil return, because part of what happens is if we drop that condenser water too low, the adductor system can't recover the oil back properly because we're using hot gas off the condenser to feed the adductor circuit. So if we do not have enough velocity on that hot gas, we cannot properly create the Venturi effect, the siphoning effect, to draw that oil latent refrigerant back off of our evaporators, which then allows it to stack up. Or if we have a gas pump, being able to properly push that that oil latent refrigerant back up into the compressor, an RTHD example. That's the consequence of getting too low. So usually with those, 70 degrees is about as low as you can safely operate. And I personally may set a minimum, or the lowest it can go to about 75 on a machine like that. I personally like to play it a little safe, but I'll set the maximum that one can go to like 85, maybe even 90, depending on the circumstances. At that point, it'll control that algorithm, wet bulb plus 5 equals your output within this window. The control system can vary the fan accordingly, and then we're not actually putting any more load on the fan than we absolutely have to make leaving water set point, which allows us to not have to run the fan at 100% all the time and still get the maximum amount of leaving water temperature, the lowest value we can get for that chiller. Now, if I was dealing with like a YK, those can operate at a much lower temperature, but they don't do quite as well at the higher temperatures most of the time, especially if I've got a site that doesn't typically load that chiller up all the way. So with a YK, I would set the same formula as to how we're calculating it, but I would set that lowest set point minimum to about 65. Now, York says you can go as low as 60, but I prefer about 65, but I'll cap out at 80. So I'll let that one swing between 65 and 80 instead of the 75 and 85 to 90 with a train, as are just two baseline examples here. That is my approach to this. The hardest part I've found is just getting everybody bought in on the whole concept. Not only from the facilities team, but even your automation team sometimes. Like, everybody else has to buy in that this is worth the time. At that point, it's not that expensive, and it's actually pretty easy to just roll that out and implement it most of the time. I've had a harder time getting people to understand this well enough to agree that this is the best direction forward.